Hello friends, so we are nearing the end of this course, and given the current circumstances, I am very satisfied the way the course has progressed. I am yet to check the third exam assignments, but I have a feel up till now that all of you have cooperated very nicely, and it has been a good journey. All is well that ends well, so let us end this well. So please pay attention to these last few lectures, because I am ending with this very important topics of weak convergence. In fact, in this course, all the topics that has been covered, starting from the definition of probability, properties, expectation, and leading to the different notions of convergence, moments, moment generating functions, everything. This course forms the basis of any course in probability and statistics that you are going to do. If you're strong in these areas, if you read these materials several times and then further try to solve problems, then this will be a good investment for you in the future. That I can say with assurance. So let's now continue with our weak convergence discussion. So this is the third type of convergence that we are studying. So here we are not talking about convergence of xnw's to xw's, or probability that xn minus x greater than absolute difference between xn minus x exceeding some epsilon, that probability going 0. No, we are not saying that. We are talking about convergence in the sense of approximating the probability distribution of xn by that of some random variable x whose distribution we know. That is the idea. So we had a definition based on the distribution functions. Now that definition is useful, but that is not always very handy when it comes to solving problems or proving weak convergence. So there are several equivalent definitions, so 5 of which I have mentioned, which are very relevant. So the first is that xn converges to x weakly or in law if and only if. So the first condition is that expectation of gxn goes to expectation of gx for every bounded continuous function g. So take any bound. Here on g there are two conditions that you cannot relate: bounded and continuous. Okay, so if you can say that expectation of gxn goes to expectation of gx as n tends to infinity, then it is the same. You can prove that this implies and is implied by the weak definition, the definition of weak convergence that you have seen in the last lecture. Now here I will take 1 minute and go to this remark. I had made a remark over here. Okay, it seems I had not saved. Anyway, the point is that I cannot drop this condition boundedness from here. Why? Because if I drop this condition boundedness, then it will mean that expectation of xn goes to expectation of x. Okay, for example, you can take gy equal to y, but that need not happen. Convergence in law does not necessarily mean that expectation of gxn should go to expectation of x. So you know that, right, that even when you had almost sure convergence, xn goes to x almost surely, then also expectation of xn does not necessarily go to expectation of x. There you need dominating conditions. So therefore, without these bounded conditions, there is no reason for expectation of xn to go to expectation of x even when xn is converging to x. So convergence in law does not imply that the moments, that is, suppose you take gy equal to y to the power k, then what will be, so this is small gy, I mean this g only, gy equal to y to the power k, then this will be expectation of xn to the power k. This is a kth order moment, so that will need not converge to expectation of x to the power k. Okay, so that need not happen. So that's what I am saying. This is a continuous but not bounded function, so this will not be included in this condition. Okay, so this is a, now I must tell you this, that this definition is the most general definition of weak convergence. So here in this course we have said that xn's are random variables, means what? They're real valued functions on a measurable space. on a probability space. But you can have a much more general conditions. That means a random variable may be vector valued, so it may be defined, it may be a mapping from a probability space to an Rn, or it may be even functional valued. That is, xn may be mapping from a probability space to a function space. So in such cases, this is the only definition, the definition 1, that becomes handy and straightforward to define, because G is for every, I should say, real valued bounded continuous function G. So then what happens is, then if xn is vector valued, or xn is taking values in an infinite dimensional space, then defining its distribution function is extremely difficult. You cannot do that. So in that case, we define it in this way only. That is the most important definition actually. So here what is important? Bounded and continuous. Now immediately from it followed from this definition that if you take the characteristic functions of xn, so expectation of e to the power it xn, that should converge to expectation of e to the power itx for every t. Now from this part will immediately follow. Why? Because ultimately what is this part? This will be expectation of cos t xn plus I sin t xn. So cos and sin are both bounded continuous functions. So 1 will imply 2, but the fact that 2 implies 1, that is not so trivial. So you can and third is that if fny is, if xn is a continuous or a atomic distribution random variable with the probability density function or mass function fny, and fny converges to fy, where fy is the density or the mass function of x, then also so pointwise convergence of the characteristic functions or the pointwise convergence of the density or distribution functions imply weak convergence. However, remember that when you are defining weak convergence by in terms of distribution function, then you don't need pointwise convergence, then you have to define convergence at every continuity point, right? Remember that, right? These are equivalent, these are 3 equivalent ways of defining and proving weak convergence. These 3 are extremely useful, and then these 2 are also there. You may have a look at them. You may find it a bit difficult. So for every open set O, open set of here, open set of real number with respect to the usual topology, openness, the mane তোমার এই যে mod x minus y যেটু মেট্রিক আছে with respect to that topology, I am talking about open set. So now the A2 liminf is greater than equal to Q, that comes actually from Fatu's lemma. So if you see, this is similar to Fatu's lemma, and the A2 opposite to hold this, because every complement of an open is closed. So again 5 follows immediately from 4. As of now, you can just have a look at 4 and 5, but for you these 3 conditions will be, first 3 would be the most useful. So I'll explain with example. So one example that we had already done is that suppose xn follows binomial distribution with parameter n and p. Then you know that as n tends to infinity, p tends to 0, and such that np tends to lambda, that is p goes to 0 in the same rate as n, as 1 by n. So then np goes to some constant lambda. Then we have proved that this formula would go to lambda to the power y factorial to the power minus y, where y is any positive integer. This goes to 0 as n tends to infinity. To my copy, this goes to 0 as n tends to infinity. So you see, what is this? This is the e to the power minus lambda to the power y by y factorial. This is the probability mass function of the Poisson distribution. This is the probability mass function of the binomial distribution. So you can see, this is the statement that I am using here. A2 whole fny. So the left hand expression is the fny, the right hand expression is the fy. Since this is happening for every y, under this condition we can say xn converges in law to a Poisson random variable. Okay, so here I am showing the application of weak definition of weak convergence, but here I am using this third condition. So pointwise convergence of the probability mass function implies. Now comes probably the most important result in probability theory, that suppose x1, x2, xn are IID mean zero random variables, square integrable, that is they have finite variance. Then I am interested in the weak convergence of 1 by root over n, sample mean na hoy, 1 by root over n x1 plus x2 plus xn. So you have seen and known that if these are IID normal, then you can compute the characteristic function and verify that then yn is also normal. Now what happens, but in ইয়াত মই normal বুলি কোৱা নাই, I am only telling you that they are IID with mean zero and finite variance. Now if I want to compute the characteristic function of yn, then you know this rule, then it will be t by root n, it is like the a raised to the power n. And so now this part of the math I am skipping, so that if you are interested you can do it, because characteristic function means what, e to the power it a2 whole phi is the characteristic function of x1. So it will be e to the power it by root n x1. So then you expand it. So first term would be it into expectation of x1. Yeah, so sorry, the power went off. So then we can prove that this goes to e to the power minus sigma square t square by 2 as t tends to infinity. This math I am skipping, this involves some work, but let's skip this. The main point is that the limit, what is this limit? This limit is the characteristic function of normal distribution with mean zero variance sigma square. So now what condition we are using? Now we are using the statement 2. So what we have proved is that if the random variables have mean zero and finite variance, then the characteristic function of this yn converges to pointwise to the characteristic function of normal distribution. Therefore this converges in law to the normal distribution. So this result is known as the central limit theorem. Here the most important condition is that the random variables have finite variance. If you drop this condition, then this CLT may not hold. So I am giving you an example. So suppose x1, x2, xn are IID standard Cauchy or student t with 1 degree of freedom random variables. So you know student t with 1 degree of freedom means no moments will exist. Student t with mu degree of freedom means the moments only of order up to mu exist. So now what is the characteristic function of this mean? So here I am giving you a hint that, so this you may not know, that the characteristic function of the standard Cauchy distribution is e to the power minus mod t. Okay, see, remember that a standard Cauchy is a symmetric distribution. So students t is a symmetric distribution, so its characteristic function will be real valued. You remember that, I hope, right? One of the properties of characteristic. So this is like e to the power minus mod t. So you use this, and the straightforward calculation shows you that for every zn, then the characteristic function will also be this is the old formula for generating functions of the sum of IID random variables that I am using. So this will be mod of t by n whole thing raised to the power n. So that will be again e to the power minus mod t. So the interesting result is that when xi's are IID standard Cauchy, the mean is again the same distribution. So for every n, Zn follows standard Cauchy. So since for every n, Zn follows standard Cauchy, so by the straightforward interpretation of weak law, so where does Zn converge? Obviously to that common distribution, standard Cauchy, because every Zn is known to be standard Cauchy random variable. So it converges to a standard Cauchy random variable. So now if I but this is the distribution of 1 by n summation of xi. So now if I look at 1 by root n, so this will be root n times Zn, where Zn's are converging to standard Cauchy. So in this case, obviously the limit will not be normal. In fact, it will not converge to in any sense, not even in the sense of improbability or in any other sense. So you see here that the central limit theorem fails. Why